Okay, morning. Let's start the lecture. We'll finish the design for welded joints today. Okay, so then we only have one more content, which is the spring, and we'll cover that next week. Okay, so just a quick review at here as to how we deal with welded joints. Okay. As I mentioned in the previous lecture, the welded joints we're looking at, okay, is mainly the fillet type of welds. Okay. And when it comes to the fillet type of welds, we use a conservative model to derive the stress, okay, for the welded joints. So the conservative model we use is basically we cut a cross section at the throat area, right? So this is the fillet weld. So basically, cut a cross section at the throat area. Then it explodes the whole external force at the throat area. Then we only consider the shear stress caused by that force. And that turned out to be a conservative model. Okay, then the mathematical derived maximum. Okay, so that's ideal. And the first case, when we derive the stress, in the first case, look at a so-called in-plane torsion. So this is the case here. We call that the case number 1. So in-plane torsion. So in-plane torsion, what does that mean? Basically, you can also imagine this. Here's the F. Here's the welded group. So the weld groups and the F, they are in the same plane. Okay? Yeah, they're in the same plane. And the F will try to cause a rotation of this welded group right here, okay, about the z-axis. Okay. So the whole idea of your welding that plates or you're applying the welds is to do what? Is to resist the rotation, basically, right? Yeah. And to resist the rotation, then there's a very important parameter, which is the polar moment of inertia of this weld group, J. The higher J, basically, the higher resistance that you have for resisting the rotation. That's what the moment inertia is for, right? Yeah. So that's the first case, in-plane torsion at here. So for in-plane torsion, first step you need to identify is which location is the most critical location. The critical location, basically, that location has the maximum stress, right? And apparently, I need to turn around that. So apparently, this location has the maximum stress. So all the locations are the same shear stress due to the shear force. But only at this location, the R is maximum. So then you have this tau double prime becomes the maximum here. So if you recall, the tau prime is called primary, and tau double prime is called secondary. Okay, they are all shear type of stress, right? Yeah. And the secondary one here is actually basically equal to MC or MR over J. So R is this, and J is the polar moment of area for this weld group. So it depends on how you weld. Maybe you weld like this, maybe you weld like this, or maybe you weld like this, or maybe you weld it all around, square, right? So it depends on the type of weld, your weld group, then the J will change. Okay? Yeah. So how do we determine the J then? We determine the J based on table 9-1. Okay? So 9-1 doesn't give us the J directly. It gives us this so-called unit second polar moment of area, JU. Okay? So it gives us the JU at here. So it depends on the type of weld or type of weld group that you apply. You find the corresponding JU based on the proper dimension. Then your J is 0.707 times H times JU. Okay? So this is basically the idea here. Okay? The idea. Okay. So let's take a look at the example, and then we'll go into the second case. Okay? So let's say I have a plate over here, and we are trying to weld, okay, a bar, okay, a circular bar onto the plate. So here's a symbol, okay, for the welding. It has this circle here, and then has 1/4 inch like that. Okay. Yeah. So what does that mean? This symbol here basically means you're welding it all around at this location. This 1/4 inch with this triangle here. Triangle means a fillet weld. 1/4 inch basically means the H, right? Equal to 1/4 inch. Okay. Yeah. So basically, it's this dimension there. Okay, the H. Okay. So then, let's see. It's subject to a torsion, and the diameter is 3 inch. Okay, and T, let's say, equal to 11 times 10 times 1,000 pound-force inch. Okay, that's the torque. So let's estimate, in this case, let's estimate the maximum shear stress, okay, in the weld throat, right? So basically, what's the tau, okay, in the throat area? Okay, yeah. That's basically the conservative model we're considering, right? We only look at the shear stress on the throat area. Okay, yeah. So this one is actually pretty simple because tau basically equal to TR over J. Okay, so TR over J. Okay, so I didn't use the M at here. You know, you gotta basically be a little bit shift of your perspective because when I write my secondary at here for like this case, I use M. So F times the distance is M. Well, M and T, they are both basically a moment of torque, right? They're basically causing a rotation in here. And this one here is more clear. It's because there's a torque trying to cause rotation like around for this weld group. So I'll just use a T at here instead of using M. But it's up to you. Basically, for usually when you have a plate like this kind of case, I think you're going to use M, okay, instead of a T. Okay. So what will be the R value? What will be the J value then? Right? Yeah. R value, technically speaking, okay. So it's not actually just a 3 inch. It's not the radius, not 3. I mean 1.5. Not just the 1.5 of the bar, because okay, technically speaking, you have this weld over here, right? You have the welds. So your R, more precisely, is 2 over 3, then plus half of this H. Okay, this is more precise value for the R. All right, yeah. So you have this basically a round of welds, right, at the end, and that's H. So half of the H as part of the basically R there. Okay, but generally, so what we see is, okay, you can see this is a 3 over 2 plus 1/8. Usually what we do is to simplify the calculation in the future, okay? So we can neglect this portion here if this is much less than 3 over 2, okay? So what we do is we just pick the R approximately, okay, as 3 over 2. Is that clear? Yeah, so this is R. What about the J then, right? So J, we obtain the J from table 9-1. So 9-1 and here, let's look at which one has that shape, right, for the weld group. Apparently is this guy here, right? Is this. So you grab this GU from here, which is 2 pi R cube, okay? So GU equal to 2 pi R cube, okay? Yeah. But this is not the J though, right? So your actual J is 707H times JU. Okay? Yeah. and h is a quarter. So GU is this, and R is this. So now you have all the parameters, all the values. You can calculate tau. It turned out to be 4.4 KSI. Okay? Yeah. Yeah.
What table was that?
Table 9-1. 9-1 is for in-plane. Okay? Because I'm going to have a 9-2 for the second case. Yeah. And one of the most confusing parts when I test this in the final is there's so many students, they can't distinguish between this in-plane and the next case, which is out-plane. Yeah.
Why do you use a half of a quarter if it's all the way around the box?
The weld it's at this location, right? Yeah. So you can imagine that triangle basically applied to the end of the bar at here. Then half of the triangle, which is the H at here, as basically it's the mean, right? So how do I draw this thing here? You have a circle over here. You have essentially, let's see, that's the edge of the triangle there. Then you're taking the mean.
So wouldn't that be a half, or wouldn't that just be plus a quarter?
Plus a quarter. Oh, this is R, right? It's not diameter. Well, am I right?
Yes, sir.
Yeah, yeah. If it's a diameter, you plus the quarter. So diameter would be 3 plus quarter, right?
You've got a quarter on both sides.
I got a quarter on both sides.
Radius.
So you're saying only look at one side.
Oh, okay.
No, see, this is 3/2, right?
Gotcha.
That's quarter over 2. Okay. If I got this wrong, that's wrong for many years now. Yeah. Good. Okay, so let's look at the second case now. Okay, so I'll call this case out-of-plane loading. Okay, out-of-plane loading here. So I'll draw this one here, and then you'll see why is it out of loading here. Okay, so basically, you have a plate. Okay, and then you have, let's say, some kind of a shape like this. Okay, you have a bar. So, yeah, I found probably drawing a 3D ones a little bit better. Okay, so let's say this is the type of weld you are going to apply, the type of structure. Okay, so then you apply the weld. Basically, it depends on how you apply now. Let's say we applied it like this, at the top and the bottom here. All right? Yeah, at top and the bottom. And then the force is applied over here, okay, at the tip. So the welds maybe has a notation like that, and H, something like this. Okay, yeah. So this is what I call out-of-plane loading. So why is it out-of-plane? So you look at basically what you're comparing now is comparing the weld group and the force F. So the weld group is what? It's this, right? So if it's like you have a coordinate system like this, so your weld group is over here, here, okay? And your force is over here. So you look at this weld group and F at here. So this is the plane. This is the plane where the weld group is in. And this is the F at here. Apparently the F is not in the same plane as the weld group, right? So that's what I call out of plane. Okay? Yeah. So when you see such kind of question, number one is actually you need to identify it properly. Okay? Because well, when I see a lot of examples, like if you mixed the two type of cases, you basically get everything wrong, right? Yeah, it doesn't matter how accurate you calculate it. Okay. So then, imagine this, right? If the F is applied here, then you have the weld group like this at this location and here. So what will be the free body diagram at this location? So at this location, I have welds like this, let's say, and then you have a weld at this top and the bottom. So you will have a certain moment generated based on the F. Okay, so let's call the M, and you also have a shear force acted on the weld group, right? So that's V, right? Free body diagram. And the M is pretty easy. So that's basically just F times the length L. Okay, yeah. But now you can imagine this. What does the M cause the weld group to do? It's going to cause it to rotate, right? But it's going to rotate in which axis? About this axis now, right? This axis. Okay, yeah. So that's essentially like, when we talk about the bar, you apply the F, you talk about the deflection, and that's the axis here, we call that what? Neutral axis, right? Yeah, neutral axis. So the difference is, it's this. See, previously the weld group in this plane, and you're trying to rotate in the same plane as the weld group, right? And the symbol we use that is what? Is G. Okay? So when the rotational axis is perpendicular to the plane where the geometry is in, you call it G. And now the rotational axis, right? It's basically the whole thing is rotating about this different rotational axis. Then this time we're not going to call it G anymore. We're going to call what? Use the I now, right? Yeah, the second moment of area basically. Okay, instead of calling opponent moment area. Okay, yeah. So just bear in mind the difference. Now, if I go back to this location and here, okay. So let's say here is my. I'll just redraw it here. Okay, so we'll do a stress analysis. Okay, so basically you should imagine there is this bars over here, right? There's this bar here. Okay. Now I'll pick a location, right? A critical location that give us this basically the most critical stress. It's pretty small welds, and I mean it's hard to tell which is critical, like the previous case. So you can actually pick any point, right, within the welds at here. So because the length at here will be negligible compared to the length of the bar, for example. So let's say I pick this location. Then what kind of stress exists at that location then? I have one stress going down due to that V. Okay, so we call that tau prime. Okay, then we also have a stress. Okay, again we call it shear stress. Okay, we call it tau double prime. Apparently this is due to what? Due to the bending moment M, right? M here. Okay, so this is a secondary. This is the primary. Okay, just like the previous case. So primary tau prime will equal to F over the area, the total area. Again, what does the area here represent? It represents the total throat area, right? Because we only consider the throat area. Okay? Yeah. Secondary tau double prime, and that's going to be the M, right? Time. So this is M here times what? Times half of the, basically, see, this is this time half of the distance here. Okay, so let's say half of the distance, technically speaking, you need to calculate from here to here, and then plus maybe half of this, right? Half of h. But if that half of h is very small, so let's just use half of this. So let's say this is a c at here. Okay, this is c. So times c over I. Okay, times c over I. Is that good? Yeah. So that's the two stresses. Then total stress is basically the vector addition of these two. Because these two are perpendicular, then the total stress is essentially just what? Tau prime square plus tau double prime square. Okay, that's the total stress. Okay, and we'll use this stress to compare with the stress. Okay, and then we can decide on the safety. Okay, so this one here again, it's what we call bending shear. Okay, even though it's actually a normal stress, technically speaking. Okay, yeah, but it's a fillet thread. It's a fillet weld. And we're just looking at the shear stress. Okay, so we call it bending shear. Okay, yeah. Okay, so A could be calculated easily from the geometry, and M can be calculated. C can be calculated. The I, right? Again, it's based on the geometry, right? So the I at here is called second moment of area. Okay. So it's basically, what's the second moment area? So it's like, for example, if you look at this geometry, this group right here, right? And that geometry basically it's this. Okay? If you look at from front view. And you're looking for is what is basically the second moment of area of this group about this axis, right? For this axis here. Okay? Yeah. So you can use formula to calculate, for mathematical formula to calculate this, but we're going to use table 9-2 to do the calculation for this I, okay, for the I here. So let me show you what 9-2 is for, okay. Okay, so this is the snapshot of 9-2. So not a whole picture here. There are a few more geometries at the bottom of the table here, okay? But bottom line is, here's how you can make use of it. Okay. So what you do is basically find the corresponding geometry, okay? Find the corresponding geometry, and then looking for this symbol here, this IU, okay? Which is called unit second moment of area. Okay, so that's basically, it's a quantity calculated based on the assumption that the T is 1, the throat area is a unit, 1. Okay, that's how the IU is calculated. Okay, so for example, if this is one here, it's basically d cubed over 12, right? D cubed over 12. Okay, so this is actually pretty, if you learn, if you have a bar mechanical system, and if this total length is L and this is M here, right? What's the moment inertia about this centroid or center of gravity here? Is what? 1 over 12 M L cube. Okay, yeah. But right now we're looking at is a area, okay, not the mass moment. It's the area moment. Okay, so your actual I should be 0.70 h times this IU. Okay, yeah. Was that good? Yeah. So, say for example, for this second one here, right? For the second one, can you imagine, basically visualize, what does the second one mean? Basically, if you have like the case like I draw over here, right? Like this draw here, how would that well be applied to that case? Right? So what's the second one here? Where do you apply the welds? Is it top bottom? Yeah, so it should be the sides, right? Yes. Okay. Yeah.
If you had all 4 sides welded.
Oh, there is a shape of all 4 sides.
Okay.
Yeah, I just didn't include it here. Yeah. The table 9-2? Yeah. Yeah. Okay? Yeah. Yeah.
Does I always correspond to out of plane and J correspond to in plane?
That's usually the convention. Yeah. So when you have, let's say, an object like this, right? And your rotational axis is going through this. So if this is rotating about that, there are two ways noting it. You can call this as a J, okay? And you can also call this as IZ. If this is Z-axis, you can call this as IZ. Okay? Yeah. So there is this theorem called perpendicular theorem. Basically, the J equal to Ix plus Iy. So the moment inertia about the x-axis and the moment inertia about the z-axis, you add them together, it's the moment inertia about the z-axis, which is the J. Okay? Yeah. Was that okay? So properly identify the type of loading condition. Okay? So then you can choose, you know, table 9-1 and 9-2 properly, okay? So otherwise, the whole thing will be wrong. All right, so now let's go into the strings concept, okay? Then we look at the an example, okay, altogether. Strings of welded joints. Now this one is a little bit tricky here. Is basically sometimes the textbook is not very consistent, but I wanted to be clear as what we do. Okay. Okay. So let's say this is the fillet welds here, right? This is fillet welds. Now there are actually, I would say, probably two ways of looking at the strings or looking at the welded joints. One way is we simply only look at the weld metal. Okay, so basically you don't consider the base metal, you only look at the weld metal. So what stress exists in the weld metal? And that's the feeder material, basically, the electrode. All right? Yeah. And the second one here, so the first one here, okay, so in the weld itself, let's say I call it, okay, right? So that's basically where the weld metal is. And second one here is we look at the attachment region, or something called a fusion region, okay, fusion area, okay. So basically it's this portion here, or this portion, right? Yeah, it's the two vertical location. Okay, that's where the fusion, okay, between the weld metal, base metal, and the feeder material, the electrode. Okay, yeah. So basically, the green part here is a mixture, right, of the base metal and the feeder material. Okay, yeah. So the strength of the welded joints should come from actually a combination of this base metal and the feeder material. Okay, yeah. And when we talk about the welded joints, it should come from both material here, right? Yeah. But first of all, what we need to know is we need to look at this. First of all, we need to look at this. What's the strength, okay, for the electrode? Okay, we need to look at the strength of electrode first, okay, and then we'll identify the strength of material, the base of material, and that's easy because you know that. Then you can look at the table here, right? Yeah. So strength for electrode. This one you need to look at the table 9-3. Okay. So I'll just show you what the 9-3 is. Okay, it's this table here. Okay. So for this table here, it's pretty easy to read it. Okay, it always starts with my pen's not working. My pen's not working. I don't know. Okay, let me close this. Open it again. No. Oh, so the button works.
Can you turn the pen off?
Pardon me?
Can you turn the pen off?
No.
Take the battery out and then put it back in.
There's battery, right? Yeah. Sounds fine. Oh, there we go. Nice trick. Okay. So where am I? Paste. Oh, it didn't paste that one there. So maybe I'll just look at this one here. So okay, it always starts with the letter E. There's just a little wing there. It always starts with the letter E there. And the first two digits is what you're looking for. Okay, so the first digit indicates it's a tensile stress. Okay, that's SUT. Okay, this is SUT here. It's not exactly like the first, but like for 60 here, it's actually 62. Okay, but if you use 60, I'm not going to count it wrong here. Okay, yeah. And the second column is this SYT. Okay, it's the yield strength. So it's these two columns. It's what you're looking for here. Okay, that's this strings here. So for example, I'll just write it down here, 60 here. So you're looking at SUT equal to 60 KSI. Okay, and SYT is 50 KSI. Okay, yeah. That's the strength of the electrodes. Okay, strength of electrodes. Okay, and then what we do next is we look at what's the allowable stress. Okay, what's allowable stress? This guy is what we're going to compare with the stress we calculated, whether it's in plane or out plane, the total stress we compare with. Okay, so the allowable stress here, we use this so-called welding code. Okay, so basically we use this welding code to calculate this allowable stress. The welding code is defined by AISI, American Institute of Steel Construction. Okay, and this is from table 9-4. Okay, that's the welding code we're talking about here. So I'll show you what the 9-4 is. Here's 9-4. Okay, this is 9-4. Pretty simple. So you need to read into the subscript, the little footnote, okay, for this table right here. Okay, but overall, it gives you the permissible stress or allowable stress for different type of loading: tension, bearing, bending, okay, compression, shear. So basically, for fillet weld, here is this guy. Okay, this is the fillet weld here. And one more is this quantity. Okay. So the bottom here says this. The bottom here says shear stress on the base metal should not exceed 0.4 SY. And here for this fillet is 0.3 SUT. Okay? Yeah. So this original 9-4, okay, this guy here, 9-4, is the table for electrode only. So you have the electrode material, right? As I said here, for example, this. Okay? Then allowable stress will be, if it's a fillet, then the shear here is 0.3 times 60 is 18, like that. Okay? Yeah. So basically, this table gives you a built-in safety factor. This is 0.3, right? It's a built-in safety factor. Now, in this class, when we're going to also use this table, also apply to the base metal. Okay, so for this table here, I'll just remember this. This is applicable to both base metal, basically the parental metal, and electrode. okay, and the electrode here. Okay. So what does that mean is basically we're going to actually looking at a situation like this. You always probably have a two base metal, and then you have this electrode here, right? So then what we do is, so let's say for the metal 1 and metal 2, and then you have the electrode. Okay, so for metal 1 you have SUT/SY. This guy you have SUT/SY. This guy here you have SUT/SY. Okay, so for each one there's SUT/SY. Then when we do the comparison, or which is we're trying to find allowable stress, so what we do is we find what's the minimum value of all the SUTs. Okay, what is the minimum value of all the SYs? Okay, after you find the minimum of SUTs, SYs, we use the welding coded here, so we apply 0.3 to the actual minimum. We apply 0.4 here to the minimum of SY. Okay, then you find the minimum between these two. That's going to be the allowable stress where you use it. Is that clear? Yeah. So basically the tau allowable here is the minimum 0.3 of a minimum of SUTs, and then the 0.4 mean of all the SYs. Okay, yeah, that's allowable one here. This allowable one here, we compare that with whatever the stress we calculated from the in-plane and out-plane, and that's essentially the final results tells you whether you're safe or not. Okay. If it's come to design, then there's this situation. Design for the design. Okay. For design, it's mainly basically talking about is the H here. What would be a proper leg size you should apply for the fillet weld in order to satisfy the loading condition? That's the design for this welded joints. Is that good? Yeah. And the design is actually not too bad, because so what you do is, if H is not known at the beginning, then you know that the tau prime and the tau double prime that you calculate, they're not going to be known, right? But they're going to be what? A function of H. Okay? Then your tau total will be a function of H. Okay? Yeah. However, you do have the electrode, the base material, so you will have this tau allowable. This is known. Okay, you will have this is known. Then, if you compare these two based on a certain safety factor, then you can calculate, right, based on a safety factor. Okay, yeah. Then you can calculate your H. Okay, and then you can calculate your H. So that's the idea of the design for the fillet weld at here. Is that okay? Yeah, I'll show you an example, okay, shortly. So, so let's take a look at one example. Let's look at one example of analysis first. Okay. I have two plates. Okay, weld the two plates together. Here's the symbol for the weld. Okay. Dimension 2, 2, 6. Okay, so that's all we need. Okay, that's all we need. So, first question, okay. So, find allowable load F if the electrode is E707 7010 for electrode, okay, and base metal is one is hot rolled 1020, the other is hot rolled 1015. Okay, yeah. Just another thing that you need to note here. So I said a hot roll here. Let's say if the base metal is a cold drawn, okay, that's a 1020. So the fact is, when it comes to after the welding, then a cold drawn 1020 actually will become hot rolled 1020. Okay, so when you, if I say it's a cold drawn, but when you're looking for the property, you actually should look for the hot rolled 1020. Okay, at the weld joints. Okay, yeah. So let's see, how do I deal with this one here? Okay, here's the symbol of the welds here, right? This is the symbol here. Then we're looking for is first we need to figure out what is the tau prime and what is the tau double prime, and then figure out the total stress, right? Yeah. The weld group, if you draw the weld group here, it's two horizontal line, right? Two horizontal line here. So tell me, is this in plane or out of plane? So basically, table 9-1 or table 9-2? Let me say 1. So we come to the concept in plane, meaning the F and the weld group is in the same plane. Out plane means the F and the weld group are not in the same plane. So apparently this F and the weld group, they're what? In the same plane, right? Yeah. It's causing this weld group to rotate about an axis perpendicular to itself, okay, to its plane. Okay, so you need to use table 9-1. If I use 9-1 and if I look at 9-1, I actually don't have two horizontal lines. We only have two perpendicular lines. So what do we do? I think I mentioned this in the previous lecture. You use this basically, but you have to rotate it 90 degrees. Okay, so you use the dimension properly at here. This is B is the length. Sorry, B is the distance, and D is the length. Right? D is the length. So if I come back over here, so this is, what is B then? This is B, right? And this is D. Okay, this is D. Is that clear? The reason is, I'm trying to be specific because in this case, fine, because this is 2, this is 2, so basically it's a square, right? Yeah. But if this is not the same, if there's a 3 or there's a 4, and I find often students that don't know which is B, which is D. And guess what? If you mix that up, then the whole thing is wrong, right? So that's very critical though. Okay? Then we need to figure out the critical location. So apparently the critical location is at this edge at here. Okay, at this edge. So the centroid is over here, and this is the edge at here. So there are two stress exist at this edge. One is tau prime, the other is tau double prime. Okay, yeah. And tau prime, okay, is easy. It's F over A. Okay, we don't know what the F is yet, right? We're looking for the F. A is the total thread area, and that can be calculated based on the second column here. So 1.414 H times D. So A equal to 1.414 H times D. Okay. So in this case here, my D is 2 and B is also 2, right? Yeah. H is what? 5/16, like that. Okay. So then now you have this A now, right? Tau double prime. And tau double prime calculation is m times r over j, right? M times r over j. Now, r at here is the distance from the centroid to this location at here, right? From the centroid to the location. I think it's actually what should be easier to calculate is so be careful here. Instead of calculating tau double prime, we calculate the decomposition component of a tau double prime. So which means, what do? We need this component, and we need this component. So let's say I call this as a tau y double prime and tau x double prime. Okay? Yeah. Because the reason is, I'll tell you the reason why this is easier. Okay? Because you're going to decompose that anyway in the end. So, you see, if I calculate this tau double prime, I need to what? I need to get m, of course, that's easy. J, that's from the table, that's fine. And r, I need to calculate this portion here, right? And that can be calculated from geometry, that's fine. But then, once you get the tau double prime, you have to use the tau double prime times the cosine of this angle, you get the tau x double prime, and then times sine this angle, you get the tau y double prime. Okay? So it involves a lot more calculation. But if I look at this way here, what is the tau x double prime? Tau x double prime goes down, right? Goes down here. You have a moment applied at here. So that actually should be what? M times which distance? From here to here. Does it make sense? So it's m times what? Half of the d, right? In this case, this is in the center of the well group, and then divided by the j. What about the tau y double prime? Tau y double prime is the shear stress in that direction, and it's due to the m2. It's actually all you need is what? M times half of the b, and over the j. That make sense? Yeah. B and a D are both 2, so you can calculate. And the J is 0.707 H times JU. And JU from the table, which is this quantity. So D times 3B squared plus D squared over 6. Okay, that's JU. So now you get your tau x double prime, tau y double prime, you have your tau prime. Then the total shear stress is, so tau total is a square root tau prime, tau prime plus what? Tau x double prime square plus tau y double prime square. That makes sense, right? Tau prime plus tau x double prime square plus tau y double prime square, then square root, right? That's what you get. So plugging all of this number here, you get 9.22 times the force F. Okay, times force F. So your total shear stress on the throat area is related to the load by this relationship. Okay. The next step is, what's the allowable stress? Allowable stress, we need to figure out the material property first. So 1020 hot roll has SUT 55 KSI, SY 30. Then 1015 or hot roll has SUT 70. Oh no, that's 50. SY 27.5. Electro 7010 has SUT 70, SY 57. Okay, so that's the property of the materials, of all three materials. So our tau allowable is the minimum 0.3 SUT, 0.4 SY. Okay, yeah. Apparently, what is the minimum of SUT, which is what? 50, right? What's the minimum of SY? 27.5. Okay, so that's where you plug it in. You calculate it, you get 11 KSI. Okay, 11 KSI. So you get this is 15, you get this is 11. Okay, yeah. Then this is the allowable one. Let's say then your basically you compare your allowable equal to the tau. You solve for the F, and you get 11 over 9.22, which is 1.19 kip. 1,000. One kip is 1,000 pound force. Okay, yeah. I should see that the results coming out of here is a KSI. Okay. So that's the way of how you solve this. This is a more of analysis, or you can call it still design, probably finding a proper F here. I'll use another example next lecture to show you how to find the H, okay, based on the given conditions as a design part.